Welcome to today's free webinar brought to you by the Australian Motor School, and we're so glad to have you here today. Greg Collecutt from TUFLOW BMT is going to be joining us, and we can't wait for the discussion coming up. But you know what? The number of people across the world has been a real surprise. Look at that, just spread across the world. Get your questions ready, everybody. Get your discussion going. We'd really like to hear from you. Greg, come online, speak to us. This is fantastic. Greg Collecutt from TUFLOW. He's a senior GPU code developer. Hi, Greg.
Hello all.
And has over 25 years experience in writing scientific modeling software. Degrees in both mechanical engineering and theoretical physics, broad experience in computer-based modeling in many fields, and specialized GPU coding skills. Greg takes pride in writing efficient, get this, accurate software for solving real-world problems. I can't stress more highly having a software written in clear, efficient coding and text. It's fantastic. Why would you be doing this? First up, tell me what drives you into doing this work?
Oh, look, I just love solving problems using computers. It's a whole lot of fun taking mathematical equations on paper and turning them into code and getting solutions that would have taken millions of humans or maybe even millions of chickens to actually compute within a sensible time frame.
That's what I get from you in this little discussion an hour ago before this webinar. I just pick up somebody who gets a bit of delight about turning the most tortuous zeros and ones into useful code. Hey, what about this, everybody? Thank you for your pre-poll answers. That's really helpful to us. The last one's really interesting. If you're ploughing a field, which would you rather use? 2 strong oxen or 1024 chickens?
Oh, look, this one was a trick question. I don't think there is a right answer to this one. It was one proposed by Seymour Cray, the father of the Cray computing machines many decades ago. And I think probably at the time the intended answer was meant to be 2 strong oxen. It's all about choosing the right tool for the job. But look, if someone is going to offer to team up the 1,024 chickens for you and make them work for you, then look, that might actually prove to be a better option.
I would have thought that'd be the key point there. If you can actually harness up that many chickens, you'd be doing well. Hey, we'll keep moving because I know there's a lot to do here. Jaap van der Velde, thank you so much for your stepping in to help with questions and comments and Q&A. Thank you very much, Jaap. Come on screen if you wish. Lovely.
Hello all.
A real person, real flesh and blood. Where are you from, Jaap?
I work for BMT and I'm from Brisbane.
Okay,
in Brisbane and working in Brisbane.
Excellent.
I work with Greg directly every now and then. So,
wonderful.
Should be able to help, especially with anything compute related.
Well, thanks.
I'm not a hydraulic modeler myself.
That's
so
fine.
Specific to the modeling may take a little bit longer to answer.
Yep, no, that's fine because this is a merging of 2 major fields, IT and hydrology and hydraulics. And Greg, you're in
software engineering and IT, so I should be able to help out there.
You have an engineering IT degree?
Yeah, computer science master's.
Wonderful. Hey, just before you start, Greg, I wanted to say this, that last week, the Australian Financial Review, no less, included BMT's TUFLOW in their top 10 list of Australia and New Zealand's most innovative companies for professional services. And they received the award in recognition of the 2020 TUFLOW release. Coincidentally, Greg here today and Phil, who was to be here, sorry you can't make it, Phil, appreciate you're not well, were the leading forces behind many of the major items in that release. So it's a bit of a wind in your sails, would you say, like a bit of a lift to have the AFR.
Oh, yes, we were very, very ecstatic to get in the top 10 out of a list of 600 or so companies. But it really, we just have such a fantastic team here that Bill Syme, our fearsome leader, has assembled and put together. And honestly, we all work together so well.
Yeah, no, the team, it's a standout team. I've been working with you guys for many years, and it just shows. All right, we're going to just leave it right over to you, Greg.
Okay, well, look, it's an absolute privilege to have you all along to listen to me ramble on today. I'm going to try and convey a little bit about what I've learned over the last number of years with computer coding and where the current state of the art is at with regard to computing and how that relates to hydraulic modeling, which really is what the majority of the audience here want to know about. So as a quick summary for my presentation, I'm going to talk about just some of the trends in computing hardware, not the trends in the last 6 months or the last 1 year, but I'm talking about over the last 20 years or so, which most of you will be fairly familiar with. And then that's going to lead us all into a discussion about parallelism. So I'm going to discuss parallel code when it comes to CPUs and GPUs. I'm going to talk a little bit about memory access patterns for uniform grids versus random memory access. And then I'll move on to how the newfound compute capability really is exposing weaknesses in existing software tools, but also opening up new horizons in terms of what we can actually achieve, and how that then impacts on best practice when it comes to hydraulic modeling. I'll also talk briefly about compute cost and picking hardware for getting your compute job done, and wrap that up with a summary. Okay, so most of these bits of computing gear, many of you will have seen these, particularly the dual CPU motherboard on the left, and also the GPUs that you plug into motherboards. Some of you will also be aware of this creature down the bottom called a Xeon Phi, and also some of you might even have heard of this thing on the right called an FPGA, which is a field programmable gate array. Dual CPU motherboards have been with us for very nearly 20 years now, and really have formed the backbone of compute over that time. The CPUs have progressed over that time as well, but the rate of their progress really has slowed up a bit, which I'll discuss on the next page. GPUs, however, have actually progressed a long way, and they're no longer used just for rendering the video output to the monitor, but you can actually do serious compute on GPUs as well. Xeon Phis were produced by Intel as a competitor to GPUs for doing compute. And the advantages of the Xeon Phi was that they used pretty much the same instruction set as the CPUs used. So the Intel compilers could very, very easily offload all of your compute work to run on a Xeon Phi. But ultimately, in terms of their compute performance, they never caught up to the GPUs, and Intel, in fact, have discontinued development of them. The FPGA, the field programmable gate array, is a very, very dedicated piece of hardware where you literally reconfigure the chip's hardware to perform a calculation real time without actually having to process instruction sets. And that gives it phenomenal performance, but a little bit more limited in terms of what instructions you can pre-configure it to run. So yeah, watch this space. They might become more universal yet. At the moment, I haven't tried working with them yet, but they could become a tool of the future. So we'll just watch this space for those. Okay, in terms of trends in computing, the number one message I want to get across is that clock speeds have plateaued. And the reason for this is fundamental physics. If you think about how far light can travel in one clock cycle, if you've got a 3 gigahertz crystal clock driving your CPU, light only travels 100 millimeters at that speed. In terms of an electrical signal in a wire, it's going to travel less than 100 millimeters because it doesn't quite travel at the speed of light. It's almost. So it might be anywhere from 20 millimeters, 50 millimeters, 80 millimeters. And that's kind of around about the size of a CPU. A little bit bigger. CPUs generally about 20 to 30 millimeters across. And so fundamentally, if you want to run a CPU at 30 gigahertz, basically it means that what's happening on one side of the CPU is now different to what's happening on the other side in terms of the clock signals. And you potentially can get asynchronous behavior. So it's just fundamentally, it's very, very hard to get a CPU or any computer chip at all to run faster than 3 to 4 gigahertz. Maybe they'll improve that limit and they'll get that up a bit further for smaller chips, but it really is a fundamental limit. So what that means then is that CPUs have headed in the direction of multiple cores in order to get more work done, which basically means parallel code. CPUs are up to, I think the Intel Platinums are 28 cores per chip. AMD has a 64 core chip out now, which is pretty good as well. And they're in the price range of generally 2,000 to 15,000, depending upon what chip and which vendor you buy it from. The GPUs that are physically separate units that you plug into a motherboard and the PCI slots, they're already up to 5,000 cores per GPU. And in fact, the new RTX 3090 out from NVIDIA has over 10,000 cores, which is really, it's a staggering number of cores. And the message I want to get here is that even if a GPU core is only 1/10 as productive as a CPU core, just the mere fact that you've got 5,000 or 10,000 of them means that your GPU is going to be able to do more work computationally than a CPU. It's just the extreme parallelism that's available that's just huge. Price-wise, again, good GPUs range generally from $2,000 upwards to up to $30,000. I think that's a very rough figure. Don't quote me on it exactly, but that's for the top-end scientific compute cards from NVIDIA. We'll talk more about that a little bit later on. Again, just a couple of figures to reinforce what I was trying to communicate in the previous slide. You can see here on the left-hand plot is some metrics for CPUs. The blue dots, the green squares is what I want you to focus on. The CPU frequency got up to around about the 3 gigahertz about 14 years ago, and it really has not improved beyond that in the last 14 years. Single thread performance has improved a little bit further over the last 10 years or so, but it's not the same rate of increase that we were getting back in the 90s and early 2000s, which many people called it Moore's law in terms of computer scaling. We're just not seeing the same rate of improvement with single thread performance. But what has been still improving is process scales. When it comes to actually making the silicon chips, the etching of the silicon chips is a light-driven process, and they've actually got that down now to using 7 nanometer wavelength laser diodes for producing that light. 7 nanometers is about a 50th of the size of normal optical light, well and truly into the ultraviolet and heading into the high ultraviolet frequencies. So they're able to put, you know, thousands and thousands of millions of transistors on single chips, incredible numbers, and that count has still been going up. So that's the bit that doesn't appear to have been hindered, and that's what's giving us the enormous number of transistors, which becomes an enormous number of compute cores on a chip, even though the speed of those cores hasn't been increasing. But this is all about, this becomes parallelism in terms of getting your work done. On the right-hand plot here, I've got GPU performance as a function of time. This is just an overall performance metric. It's not divided into different categories like the CPU data is, but you can see it's still continuing to accelerate in terms of growth. It's almost looking exponential still. Okay, so when it comes to being able to write parallel code, it's harder than you might think. And believe me, I'm talking from experience there. I've been doing this for over 15 years now, figuring out how to write software that works in parallel. Sorts of codes that can be converted into parallel fairly easily are things like multi-dimensional Fourier transforms, explicit finite difference and finite volume schemes, matrix assembly. But matrix factorization in terms of the lower upper diagonal factorization or other matrix solution schemes are not so easy to parallelize, because when you want to do a certain row in the matrix, you can only do it after you've done the previous row. And so your code becomes quite sequential in its list of operations, and that's difficult then to parallelize in a way that's strong and robust. So my whole point here is that implicit schemes, which tend to work on solutions to matrix problems, implicit schemes are difficult to parallelize. And that means then that explicit schemes are given an advantage in today's computing environment. Explicit schemes, as Bill Symes said last time, they're not quite so mathematically elegant or beautiful as some of the implicit schemes are, but they're a whole lot easier to implement when you've got thousands of cores available to do your work. very much a brute force and ignorance method, or maybe we'll call it a brute chicken ignorance method. Okay, so here's an example. This is a two-dimensional problem. Now, I'm sorry, I'll just backstep one point. From here on, I'm really only going to be presenting results for CPUs and GPUs. And that's because, as I said, the Intel Xeon Phi has been discontinued because it really couldn't keep up with NVIDIA's platforms, hardware. And the field programmable gate arrays are not a mature technology yet when it comes to general compute. They're getting there, but they got a little bit more to go. So just concentrating on CPUs and GPUs, and I just want to start comparing how well each of these works with parallel code. In this case here, we've got a numerical relaxation problem. So the yellow square in the middle becomes the average of the 4 blue squares around it. And this problem is performed out of place. So you have, you keep 2 copies of your grid. You have one grid as your input, and then you compute a new grid as being the output. And then you can perform multiple iterations by moving on, by copying the grids and going from one grid to the next to the next. Now I've got 0s and 1s around the outside. They represent the boundary condition for this problem. And after you've repeated many grid iterations, your solution will actually converge to what is Laplace's equation solution for this two-dimensional heat conduction problem. I've given the example C code here on the right as to how you would compute that. And I've coded this up to run both on CPU and GPU, and we're going to look at the performance of each of these hardware platforms for this problem. Okay. So here is the CPU performance. This was on an AMD Threadripper CPU, the 2990WX, running at 3.8 gigahertz. The horizontal axis for this plot is the number of elements along one side of the square, so that the total number of elements in the square is actually the n squared. And then the y-axis for the plot, which is shown in log scale here, is the number of cell iterations performed per second. So it's the number of cells in the board times the number of overall board iterations per second that you achieve. Now what you can see here with this blue line is there's 2 parts to it. There's the left-hand part from about, oh well, I've got the pointer, I'll show you, the L1 cache region. This is where we're actually achieving maximum performance on a CPU. And it's when the problem is very small. We've only got 100 cells on each edge. And this is because all of the memory required for this problem fits within what's called the L1 cache on the CPU, which is actually attached to one core of the CPU. The memory is really, really local to where the computer operations are being performed. Once your model starts to get bigger, once you get beyond 200 cells on each edge, it can't fit in L1 cache anymore, and progressively more and more of the problem has to be stored off into L2 cache, and then beyond that it goes to global memory, which are the plug-in sticks that go on the motherboard, which are physically a long way away from the CPU, and it takes a fair bit of time to send and receive memory requests or data to and from those storage sticks. And so what we see is the steep downhill trend. As the problem size gets bigger and bigger, it just gets slower and slower. And in fact, I thought it might plateau out a bit beyond n of 1,000, but it still seems to be showing some decrease there. And that's a sad thing for us hydraulic modelers, because we're not interested in modeling problems with 100 cells by 100 cells. That's not going to cut it for issuing a report to a client when they can see the pixels as big as thumbnails on the page. It really needs to have much more resolution than that in today's computing environment. But what we see here is this downhill performance in CPU computation. We can take the same code and we can parallelize it to use multiple cores of the CPU. So in this case, the new blue line I'm showing here is when we use 16 threads on the CPU. With 16 threads, what we find now is that we get an uphill trend in the small model sizes. As the models get bigger and bigger, it gets more and more efficient. And then it starts to trend downhill again as the model extends beyond the available memory required on the CPU. And the difference on average between the blue line and the dotted black line for big models here is about a factor of 6. Now, this seems terrible that we throw 16 cores at it and it doesn't run 16 times faster. It only runs about 6 times faster. But that's unfortunately what actually happens in real life. And this is quite indicative of what happens with most computer software, that even if you've got 32, 36, 64 cores, it's really difficult to get beyond about a 10 times speed up of your algorithm on CPU. The parallelisation, it actually runs into a bottleneck in terms of transferring the memory from those plug-in sticks to the CPU. You've got enough cores for doing the work, but you don't have enough memory bandwidth for getting that data to and from the global memory on the motherboard, and that's quite a problem. So I also coded up that same problem to run on GPU. And now we get a very different looking picture. This blue line is the GPU performance in terms, this is on a Titan 5, a GTX Titan 5, which is actually about 3 years old now, technology. We got a very steep uphill trend from small model sizes as we get bigger and bigger and bigger, and then it plateaus. During this uphill trend here, that's just to do with, there's a small amount of time delay with what they call the kernel launches on the GPU and data movement back and forth. It takes a certain amount of time just to harness all your chickens to get them ready to go. But once you've got them harnessed, then boy, do they go. They really fly. And in fact, what's happening here for really big models is once you're out at 10,000 cells by 10,000 cells, so this is a 100,000 cell model, the GPU is achieving 600 times the performance compared to 16 threads of CPU. And this is for a GPU that's 3 years old. It's just absolutely phenomenal. So it's got some promise for the future, but how that goes with real codes, we'll investigate that a little bit further on. Now, most of you will be watching this webinar on an LCD laptop or LCD screen of some sort. I don't think even a single one of you will still be watching it on a cathode ray tube. When you think about an LCD screen, you think about a whole lot of pixels in a regular 2D grid, much like a regular grid that's used for hydraulic modeling, like in TUFLOW Classic. And of course, what powers that image on the screen is the GPU. That is what they were designed for. The graphics processing unit was designed for producing the image on the screen. So it would only be natural to think that GPUs are good for working with 2D grids. It's to do with whether or not the memory access pattern is predictable or unpredictable. Here, you can see on the slide here, I've got on the right-hand side, I've got a TUFLOW FV mesh. This is a finite volume mesh made up of quads and triangles. And on the left-hand side, I've got a quad tree mesh. So these are all squares, but there are squares different sizes that have refinement applied in different regions. In both cases, when you move from one cell to the next for computing the fluxes around the boundaries, you are sending and receiving memory requests to global memory, which are not strided by the same access pattern as the previous cell. So the memory controller has great difficulty in predicting which piece of memory you're going to be wanting to get next. When you're doing 2D grids, a regular two-dimensional grid, like the LCD screen pattern, when you're doing a regular grid, the memory access is predictable. You can move memory around in large strips and blocks, and it's very easy. When you've got a flexible mesh like this, it's much more arbitrary, and your memory controller has issues with efficiently fetching the memory that you want. So I'm going to mimic that by taking this previous problem that I showed you, the numerical relaxation problem for Laplace's equation, and instead of using the 4 blue cells that were adjacent to the yellow cell, I'm now going to use randomized vectors or randomized arrays for that pattern of blue cells. So as we change the yellow cell to a different place on the grid, it's going to have a completely different access pattern for which blue cells are going to lead to each result. I've given it the nickname scrambled egg test because it really is just messed up memory access. Now these are, I've just put all the results on a new graph here. So I'll go back right to the beginning. This fine dotted line down the bottom was the next line up here, the second line up from the bottom was single thread with regular memory access. And then when we changed to irregular memory access, the performance, this is CPU, the performance dropped by about a factor of 5 or so in terms of the number of cell steps per second that it was able to do. And that's quite an expected result. When we look at the 16-thread CPU performance, it also drops by about a factor of 5 in terms of difference between regular grid and irregular grid. When we look at the GPU performance, it seems to have been much harder hit. And perhaps this is expected because, like I said, GPUs are designed for working with regular grids. Its performance has actually dropped by more like a factor of 50 from best to worst between regular grid and irregular grid. But we started from a position of being 600 times faster. We're still in a position of being 30 times faster than 16-thread CPU, even for the arbitrary memory access. So in summary, yes, arbitrary memory access, GPUs don't like it very much, but even still, they're a whole lot faster than CPUs. So let's wrap all that up. CPUs don't show linear scaling when you increase the number of cores that you use for a problem. Even for simple problems, they don't show linear scaling. With very, very, very careful coding and simple problems, you can get them to be linear, but you've got to manually control memory movement around and do everything in little tiles. And it's computationally, it just makes your code 10 times bigger to make it work. CPUs show a loss of performance, a downhill trend when your model gets bigger and bigger, and that's because of bandwidth available to global RAM on the motherboard. Whereas GPUs do the opposite. GPUs show a gain in performance when scaling to large models. For a number of reasons, it's because of the enormous parallelism. It's also due to a huge memory bandwidth available between the GPU and the RAM. NVIDIA designs everything on the GPU, so they make sure that everything is well tuned and works together. The other factor that comes into it is this thing called thread oversubscription, which if you really want to learn about that, I can explain at the end, but I'm going to run out of time if I try and explain it now. There's a fair bit to it. Both CPUs and GPUs show a loss of performance when you go from uniform grids to unstructured grids. And when I showed the result before that GPUs dropped by a factor of 50 times in performance going to an unstructured grid, really that was specifically for that small problem. When you've got a larger, more complex code that has literally can have 1,000 lines of instructions within one GPU kernel, then that drop in performance isn't nearly so marked. And we'll see that later on when we look at some real code results. And that GPU performance on a large unstructured grid still far exceeds multi-core CPU performance. So here we go, real codes. Now the only 2 real codes I've been able to test, 3 real codes, are TUFLOW Classic and TUFLOW HPC. And TUFLOW FV, which is our finite volume code, the arbitrary mesh model. So for uniform grid, we'll look at TUFLOW Classic versus HPC. TUFLOW Classic is written in Fortran. It was written by Bill Syme using Stelling's ADI scheme. It uses a matrix solution and it can only run on one thread. I've talked with Bill a few times about whether or not we can parallelize it, but it really looks like it would be a tremendously difficult task. And for our particular model, 3 million cells, urban direct rainfall, so it has nearly every cell in the model is wet, and it also needs to use smaller time steps than perhaps you would use for riverine flooding models. It completed the problem in 121 minutes. Now, the HPC code is an explicit finite volume solution based on the square cells again. That code is this very same source code is compiled both for execution on CPU as well as for execution on GPU using CUDA. When I run it with one thread on CPU, it takes 264 minutes. Now, this is an example of how the Stalling scheme is mathematically a whole lot more elegant than a brute force and ignorance finite volume, explicit finite volume approach. But when you're then able to throw thousands of cores at it with a GTX Titan, then the compute time dropped to 3 minutes, which is a speed up of, at least if we compare the same code just run on one thread CPU versus a GPU, that was an 87 times speed up is what we achieved from one thread CPU to GPU. And it's also a significant speed up over the original TUFLOW Classic scheme. When we look at a structured mesh example, using TUFLOW FV, a 3D estuary model, it's got 1.6 million cells. It has salinity, temperature, water quality components. This is using the TUFLOW FV code. The original code that was written by Ian Teakle was all in Fortran and could be run on one thread CPU or up to as many cores as you've got. So one thread CPU was nearly 800 minutes. 16 thread CPU was down to about 107 minutes. So that's about a factor of around about 7, just a touch over 7 times faster running on 16 cores. Now that code, I've also rewritten that in C++ and compiled with the NVIDIA's CUDA compiler and can run on a GTX Titan, and we've got that down to 14 minutes. So that's actually, in terms of comparing one thread CPU versus a GPU, that's a 56 times speed up. In terms of how fast it runs on one GPU compared to as many cores as you've got of CPU, it's about a 7.6 times speed up. So that's where I was saying before that even on an arbitrary mesh problem, GPUs still outperform multi-core CPU just hands down. This little image that's in here is actually out of NVIDIA's visual profiler. It's showing us the kernel start and stop times for all the different kernel launches in a piece of solve for the TUFLOW finite volume solver. And what I've highlighted there in the pink box and the magenta box, I'll just put my mouse cursor on it, is the sequential list of all the kernels that are called. It's got a number of steps for an internal mode, and then it's got an external mode, other way around, sorry, number of steps for an external mode, then an internal mode. So it's a split mode solver, so it's computationally quite efficient. But importantly in there is that there's almost no white space in there. Nearly all the time is spent doing GPU compute. If someone else has a software that you only see your 2 or 3 times speed up between their CPU version and their GPU version, there is a possibility that their GPU version is not fully utilizing the GPU. I'm talking about a good GPU here, a good CPU to good GPU. It's possible that's not achieving a high utilization. If that's the case, if there's lots of white space in their utilization here where the GPU isn't doing useful work, then it means that later on, when you spend more money to buy a new GPU that should be 50% faster than the one that you've got, what you'll find is when you run this piece of software on it, this hypothetical piece of software that only gets a 2 or 3 times speed up on GPU, if you run the software on it, you might only see a 5% improvement in your runtime, even though you've spent a whole lot of money to get a GPU that was supposedly twice as fast. So this is where it's really important to have an efficient GPU utilization in order to have code that is future-proofed, that is going to work well with new GPUs when they come out. Okay, I need to rattle my dags and get a move on here. Very Australian term. Newfound capability helps us with the GPUs, really opens up some options here. We can get faster model turnaround during your calibration process. If you're running Monte-Carlo ensembles to get statistics, like you might do for using the Australian rainfall and runoff guide, then you can run more on ensemble members and get better statistics. Alternatively, you can run longer duration events, and this opens up areas of water quality modelling as well, because you can, instead of just running 1 month or 2 months of an estuary, we can now run years of an estuary very easily. It also enables smaller cell sizes to get better resolution pictures. Everyone likes higher resolution pictures. The question is the higher resolution real in terms of its accuracy or not? That's something you need to think about. And also whole of catchment models are now tractable. But when it comes to this smaller cell size for higher resolution, it can expose weaknesses in your hydraulic scheme. Some solvers will go unstable when you run smaller resolutions. TUFLOW Classic is an example of that, where we've had models that when you reduce the cell size, sometimes stability problems can result. And usually they're fixable by some other configuration in it, but you have to track down the problem and sort it out. How well do your results converge when you're looking at maximum water levels or flow rates through a particular cross-section across a primary flow path, and then you run your model at different cell sizes? Are they heading towards the same result? And that ties in with your turbulence model. How good is the turbulence model? Is it appropriate for models with small cell sizes? Just as a very quick example of this, here is a model here which is just of the section of the Brisbane River going through the Brisbane CBD. It's about 11 kilometres of river, for which we do actually have accurate historical information from the 2011 flood. 9,000 metres cubed per second going down the river. Very, very, very much a steady state model. We knew that that was exactly what was going down, and that flow was held for hours at a time. And we also knew from recorded data that there was almost exactly a 4-metre head loss along that stretch of river. Now, what we're plotting here is the pink dotted line here is our predicted 4-metre head loss. I've got head loss on the y-axis, and I'm looking at how the results converge with cell size. When we used the Smagorinsky turbulence model, what we found was that as you reduced the cell size, the head loss reduced. And basically, this is an inherent problem with the Smagorinsky turbulence model, that when you make the cells smaller, the turbulent viscosity drops to 0. And the end result is that it didn't matter what coefficient you put out the front of it for the proportional term of the Smagorinsky turbulence model, the results always converged down to an incorrect result. You couldn't even adjust the turbulence model to get it right. You would have had to add a whole lot of constant offset to it. So that sent us in search of a new turbulence model, and this is where we eventually came across the Wu 3D turbulence model, which now shows much, much less cell size sensitivity as you go down to these finer cells. You see, getting results at 10 meters, 15 meters just wasn't possible before using GPU technology, because it was just models took far too long to run. And not only that, but with this Wu 3D turbulence model, we're able to get the parameter that gives us about the right head loss as well. So this is where, using GPUs has exposed a weakness in an existing scheme, and it sent us in search of improved turbulence closure models to help improve the scheme. And number one, get it more stable, and number two, get the right results out of it. Another area of new horizons that this is opening up is with GPUs, whole of catchment modeling becomes tractable, because previously the runtimes were too big, but now they're okay. This is an example here of a catchment in Wales. The top set of plots here, the solid red line is the actual flow rate observed at the cross section, but it's a flow rate that's probably been computed from a water level interpolated into a rating curve. Now these different colored lines here, the pink, blue, green, yellow, are the predicted flow rates at those cross sections out of TUFLOW, the TUFLOW HPC solver for different mesh sizes. So you can see as we're decreasing the mesh size, getting more resolution. It looks like it's headed in the right direction. We're getting an earlier rising limb on the flood peak, and the shape is improving. But there's still a lot of sensitivity, and you'd end up concluding from that you need to be running the model at 1 metre resolution to be getting good results. But we've introduced the subgrid sampling into TUFLOW HPC now to generate cell volume storage curves and phase flux rating curves. Now what you can see is that the response time for the catchment is now really, really good. The timing is excellent. The shape of the peaks is excellent. The double hump is there, but also the cell size sensitivity has disappeared, almost disappeared. So from that, you could probably conclude that I can run that whole of catchment model with a 20 metre cell size, and my results are sufficient quality to present. And of course, the 20 metre cell size combined with a GPU solver means that you can run this whole of catchment model now in a sensible time frame, whereas what would have perhaps taken a month or more to run is probably now back to just a couple of hours runtime. With this newfound computing capability, it's not like it's been a trouble-free road to get there. There have been humps and bumps along the way, like I said, about finding weaknesses in existing hydraulic schemes. Just because we've got great computational ability and great software doesn't mean that the role for hydraulic modelers is in any way diminished. We need modelers who are still curious, pay attention to detail, investigate problems when they come up, can spot poor results. Very, very important that you check your results and question whether or not you think they're right. We need hydraulic modelers that take software tools that they use and put them through their own tests so they understand just how accurate they are or aren't. We need modelers who don't get stuck in a rut in terms of software, but are prepared to move with hardware and software in order to get their modelling costs down and improve the quality of their results and what they're able to achieve within a certain time frame. We need modelers who understand that, the balance between accuracy and cost. My mantra in life is better late than wrong. But you need to get a good handle as to whether or not your results are wrong quite early on. Okay, just a very quick note on costs. I need to wrap up. In terms of GPU compute and CPU, both for CPU and GPU, you can either be heading off to the cloud to run your models there and ship the results back, or you can buy your own hardware and stick it under your desk or in your own little server room if you've got office space, and do that. Now, what we find is that, just as a quick example, on a cloud provider, you might spend $2 per hour for an entire node with 36 cores. You hire the same virtual machine with access to a late generation GPU like a Tesla V100 or something, you'll be paying about $4 an hour. If the software runs 4 times faster on GPU than on multi-core CPU, then the cost to get your solution is now about half. Doing it on GPU, the cost is about half as much compared to CPU. If you buy your own hardware and stick it under the desk, you might spend $12,000 on a dual-core, dual CPU desktop, or you could buy a single CPU desktop and drop in 4 gaming GPUs, like the RTX 3080, and you'd get a good machine there for about $18,000 that's got 4 GPUs in it. And if you can achieve a 4 times speed up on GPU over multi-core CPU, then your overall solution cost is now about 1/10 going to GPU compared to CPU. And the reason that it's so much better than the 1/2 when you're on a cloud solution is that you've bought gaming GPUs that are relatively cheap. In data centers like Microsoft Azure and Amazon Web Services and others, the NVIDIA has a license agreement for the use of the GPU drivers that actually constrains them to only use the Quadro and Tesla series GPUs, which are very much the flagship scientific grade GPUs. They're quite expensive. They're designed for 24/7 operation. Perhaps a gaming GPU isn't. But having said that, we've been using gaming GPUs for years and the failure rate is relatively low. It's not really a problem. So yeah, look, it's definitely cheaper to buy your own hardware and use that. But it's always an option maybe to buy enough hardware to cover, 70%, 80% of your workload. And then if you get a big job comes in, then just outsource to the cloud and accept that it does cost you a little bit more, but at least it's better that than having hardware in-house that you're just not utilizing. Summary for hardware selection, if you're wedded to doing things on CPU, you just have to be prepared that you'll only get about a 10 times speed up with multi-core CPU. It's generally better to have two 10-core CPUs than to buy one 20-core single CPU. You get more bus access between the CPUs and the global memory. A good quality motherboard and chipset is definitely important in getting the most out of those CPUs. If you've got software that's also MPI capable for distributed computing, then it's best to launch one MPI rank per CPU, with each of those ranks then being multi-threaded for use within that CPU. I can cover that in a bit more detail later if you're interested. When it comes to GPUs, the published flops are seldom a realistic guide to the performance of the GPU. The real code has a lot of if-then-else branches and other delays that slow it down. So don't so much go with published flops as the guide. Actually try and get some hard benchmarking numbers. Single precision, then gaming GPUs are cheapest. If you really, really need double precision for whatever software you're running, then you might want to consider a Quadro or a Tesla series card. They're a lot more expensive, but their double precision performance is also quite a bit better as well. But having said that, you can still run double precision compute on the gaming cards. It's not like you can't do it. They still run it reasonably well. And also think about the GPU RAM and the size of the models you want to run. If you really need a lot of RAM, then the Quadro and Tesla series cards generally give you more options for that. Okay, look, I'll leave it there with the summary page up. So, Trevor, were there any particular burning questions at the top of the list that you want me to address?
That was a fantastic rundown. It was good stuff on steroids. It was just an array. I rarely see such in-depth thinking in clear presentation. I'm not just running on here. I've heard a lot of people talk IT, but I could nearly understand most of that. I mean, I'm not an IT expert, you can tell, but it's not the issue. I really appreciate the amount of work you've done on this, and there's been a ton of questions. Jaap has been going 10 to the dozen, flat out answering questions. Thanks so much, Jaap. I'm going to hand right over to Jaap.
There's one question where I figure Greg might have some additional insights. I did provide an answer, but this is the question from 1234 asked by David De Mauro.
Okay, so sometimes TUFLOW does not employ all the available chickens your machine could unleash. Is there a way, a switch in the TCF, in the batch file perhaps, to betroth your machine's power to TUFLOW simulation and appreciate an increase in performance?
So Bill pointed out that you can use TUFLOW to control how many GPUs are used, which GPU you use and how many cores you use in your CPU. So that's a little bit about configuration. But I'm guessing what David is asking about as well is if you have a lot of cores in your GPU, but they're not being fully utilized, how can you get TUFLOW to utilize the rest of them? And I figured it's probably something to do with the amount of compute you can do in a single step, but I'd be interested to know whether there's other aspects there.
Yeah, look, the GPU driver and the onboard software on the GPU controls the launching of kernels across all of the different streaming multiprocessors that exist. A GPU might have literally, it's got like 10,000 cores, but they are configured in 32 cores per streaming multiprocessor. And each one of those, so you've then got, about 320 streaming multiprocessors. Look, they're all supposed to be working. It's not like we are deliberately cutting chickens free and not using them. We're trying to use them all the time. What happens sometimes is that for smaller models, especially for smaller models, it's just the amount of time that it takes to set up the kernel launch across all of those streaming multiprocessors becomes quite significant compared with the actual compute time. So you get this more and more of this dead white space that I was talking about in that compute timeline. For larger models, once you're generally above about 500,000 cells, and definitely above 1 million cells, that timeline should be looking at about 90% occupation with GPU compute or better. Other factors that come to it is 1D pipe network. If your model's got a very large 1D network, what happens is the 1D network is still computed with the existing S-tree solver within TUFLOW. That's not done on GPU, and the inputs and outputs to that have to be copied on and off the GPU. So if your model is pure 2D, then it uses the GPU beautifully. But if you've got a large 1D network of 10,000 or 100,000 pipe elements in it, or river elements, then that can become a problem. But this is where, these new horizons that I was talking about become important, in that because of the capability that SGS is offering, as well as now the quad tree solver, with being able to coarsen regions of your model that are not so hydraulically interesting, it's becoming more and more possible to neglect 1D flow paths as not to model them as 1D anymore, but just model everything in 2D. Even all the small tributaries, they all work fine in 2D now. Having a 1D river network I would say, is really not the best way to go anymore. So, but for underground stormwater pipes, of course, you can't get around that. You still need stormwater pipe network. Yeah, look, if your machine's got multiple GPUs, then yes, you can use device IDs equals, and you can give a list of 0, 1, 2, 3 if you've got 4 GPUs plugged in. So you can use multiple GPU, but again, I would really only advocate using multiple GPUs if you've got models that have got millions of cells, or 5 million, 10 million, 20 million cells. If you're down at 100,000 cells, multiple GPUs is probably going to be slower than running on one GPU.
Yeah, thanks, Greg. There's currently also 2 open questions that you might be able to tackle in one go. Gert Dieter is asking whether you have any commentary regarding PCIe 3 or 4 bus speed and the number of channels and modeling performance, whether you've done any comparisons. And Matt is asking if there's any recommendations about using multiple discrete GPUs versus NV-linking GPUs. Not sure whether you can tackle them in one go, but both are about the hardware selection, I guess.
Yeah, okay, look, what NV-link does is it enables one GPU to send and receive data to another GPU directly over the NV-link without having to go through the PCI bus on the motherboard. Look, with the TUFLOW modeling, whether, if you've got a model split across 2 GPUs, the amount of data being transferred from one GPU to the other is actually very small. And likewise, when you've got a 1D network in there, even if you've got 10,000 pipe elements in there, the quantity of data that needs to be shifted on and off the GPU is relatively small compared with the entire model. What we find is that there's more of a latency issue to do with configuring and executing those memory copies between CPU memory and GPU memory. It's not the bandwidth that's the problem. It really is just the latency of setting up the memory copy and then synchronizing results afterwards, making sure the copy's are correct and everything. So, and what we've found then is that we have TUFLOW can use an NV-link if you've got one installed. There'll be a message. The 2020 release will put a message in the log file saying peer access possible, and it'll use NV-link. Also for Quadro and Tesla cards in TCC mode, which is Tesla Compute Cluster mode, they can also have direct peer-to-peer access over the PCI bus as well without having to go through the CPU. Look, we've tested both of those, and we've found that there's very marginal speed improvements using an NV-link or having a fantastic PCI bus. And like I said, it's because it's not the bandwidth that's the issue. It's just the memory latency of launching the memory copy and then checking results afterwards and so on. I'm not, to be honest, Mike, that's really at the edge of my understanding of what's going on with the computer science in terms of the memory transfer, but yeah.
I guess the other question was already partially asked and answered previously about the number of buses and I guess or number of channels on the bus, I guess the bus speed. Is there anything worthwhile mentioning about that?
No, I have to apologise, but I haven't actually had the opportunity to do any benchmarking with different bus configurations. So yeah, that's actually off the boundaries of my understanding.
Typically, obviously, the number of channels will increase the amount of time it takes to load data onto the card and off the card. So it will typically affect your model runs, but neither have I. haven't tested anything with bus speed, so I can't really answer the question either. There's another question, Greg, asking whether you've been looking at the parallelizing the S3 code for CPU or converting it into GPU.
Oh, okay, yes. Look, we have talked about that internally, about parallelizing S3. Either S3 currently will do all of those 1D computations just on one thread of the CPU. And generally to date, it hasn't really been a major bottleneck. We know it is a bit of a bottleneck if you do have a big pipe network, but it's not like it takes a model that could have been run in 1 hour and means that it takes 10 hours. But yeah, we've talked about either rewriting it from ground up in C++ and compiling with Cooper so it can run on GPU. And we've talked about just trying to parallelize the original Fortran code and get that to run multi-thread CPU. But we haven't made any progress with either yet. Our development team is, we have this enormous list of tasks and features, and we continually shuffling priorities and sorting through them all, and that one hasn't been at the top of the list, but it's definitely not at the bottom either. I'd say it's about 2/3 way up.
Yeah, I think most of the other questions were answered. Maybe someone can pipe up in chat if they feel something needs a little bit of extra attention. I didn't have any additional ones that were unanswered.
No, that sounds good. Yeah. Maybe we could draw it to a close here. I appreciate there's probably a lot more we could go with. It's been absolutely mind-boggling what you've covered in such a short space, Greg and Jaap. Thanks so much. I might mention, Lloyd, thanks for your comment there. That will stay in the Q&A and it will go off to the presenters. And I think that's really crucial. You've talked about the groundwater equations and the TUFLOW equations and how you could work together. I think that's got a lot of future.
Yeah. And I will definitely, Lloyd, I'll take your question offline and answer that one directly with you. But I will say that this is something that is beginning to catch our attention, is the need for some sort of catchment-wide software that can give sensible inputs to a water quality model that runs for an estuary or a river, to have the right inputs for that. And that means solving the equations of motion of water, not just for above ground water, but of course underground water. And it involves timeframes that extends over months and years during all the dry spells. I mean, hydraulic modelers are used to modeling, 24 hours of a flood event, not 24 months of dry weather.
Yeah. It's quite different. You're quite right. Hey, right, well, we'll draw this to a close. Thanks, Bill, so much. Bill Simon, you've been on board, and so is Craig Price, strong modelers in the whole field of hydrology and hydraulics. We've appreciated it hugely. We'll draw this to a close. On-demand courses, webinars and live training, stacks of it coming up with the Australian Water School. We look forward to seeing you at the next webinar. But for now, thanks, Greg. It's been wonderful, you and your team there at TUFLOW at BMT. We look forward to doing more work with you in this webinar training professional development.
Very good. It's yes, there's other team members that are going to get their turn over the next few months as well. So
look forward to that in a big way. Tell them we can't wait. Thanks to Joel at the Australian Water School who's pulled this all together. It's been wonderful. I'm going to leave it there. So we'll say goodbye for now. And thanks for joining us, everyone. See you next time. Bye for now.
Yes.
Yep.
Thank you.
Bye, Greg.